So we're talking about a power series, and we have new ways of defining functions f of x by this infinite series. And in this case, instead of x to the n, we have an x minus 3 raised to the n. So this is called our power series. It might say something like centered at 3, or it might say a power series about x equals 3, or other common phrases that we would say of where the function is kind of based on its center point. Why do we say this? Well, yesterday we saw that for any power series, if the number that is input here, that the number that I'm raising to the nth power, if it's 0, it will converge, right? And with just x to the n, if I plug in 0, we'll get 0 to the 1, 0 to the 2, and it will always converge. In this case, I know that f of 3 looks like this. So I would just put 3 in for x, of course. And you just want to be careful about, actually in this case, we need n. Let's change the denominator a little bit. Let's say n plus 1. So of course we can't have a 0 there, because if n was 0, if the denominator is 0, it's not going to make sense. It'll blow up. So my 0th term, when we plug it in, would be some constant to a 0. It would be, you kind of have to think that if I just wrote out the series before plugging in any value, we get something like this. Oh, sorry, that should have been minus. It's minus 3. So this is our function, and of course, x minus 3 to the 0 is just 1. And so now, of course, when I evaluate it at x equals 3, we can get a better sense. If you're not too comfortable with plugging in a value right into a power series, of course, this will just be 0 to the n, which should be 0 for all the terms. You do just want to be careful about the constant term, because if we actually wrote out the function, you kind of see when I plug in 3 now, it's only the degree 1, degree 2, and higher terms. Those will all be 0, and we will just get that constant term, our 0th order term. So it converges for sure, because I can just add 1 and I can add as many zeros as I want, and we will still get 1. So this is what we mean by centered at 3. Now the interval of convergence, as we will see and describe a bit more, is going to be centered at x equals 3. And we know that for 3, it will converge. So our next goal then is to find, well, how big will it converge, or how big of a radius can we pick? What is our domain of x values that I can plug into this function? And so we call that the interval of convergence, the domain of convergence. You will see the term also radius of convergence, which is slightly different than this. Essentially, the radius of convergence is going to be determined by the ratio test, but it'll be a radius, it'll be an interval centered at a different point at 3 now. So let's see how that works. So how do we find our interval of convergence? Well, we first find our essential radius of convergence, and we do this through the ratio test. So midterm, it looked like the ratio test problem wasn't too bad for you guys. So something you want to keep working on, though. I think most people were in like the 70% range or higher, which is about where we all want to be. But it's going to be something we're going to continue practicing. And in particular, these factorials. So we'll do a problem with factorials after this. Were some common mistakes that I saw on the midterm. So for this guy, we can just write out our terms. So our an is x minus 3 to the n over n plus 1. And our a n plus 1 is x minus 3 to the n plus 1 over, now, n plus 1 plus 1. So it should be n plus 2. So this is our given term, we could call it, and this is the next term. And we want to take the ratio of the next term to the given term, and we want to take this ratio in absolute value and compute the limit. So we've got, actually, let me start a new page to give ourselves some space here. So we've got our limit as n goes to infinity of an plus 1 over an. And so we will have our x minus 3 to the n plus 1 over n plus 2. Big division sign. And if you want, put the numerator and the denominator themselves in individual brackets just to keep track of all the division signs. We've got x minus 3 to the n over n plus 1. I'm just going to ignore writing the limit there, since we can always just compute this first, take the limit at the end, just to save some writing space. And so with these guys, you should get in the habit of just keeping the numerator as it is, and then multiplying by the reciprocal of this guy. So it'll be n plus 1 over x minus 3 to the n. And so one thing I'm forgetting is we need absolute values. And we want this to be less than 1. So we are essentially declaring this ratio as less than 1. So the manipulations are still the same, essentially. Right now, we're really just focused on this left side, and we are going to declare that in absolute value needs to be less than 1. Because if I declare it as less than 1, I know it will converge by our geometric series for whatever x we plug in there. So we simplify now. I've got x minus 3 to the n plus 1 over x minus 3 to the n. That'll just give me 1 power of x minus 3. And then we have an n plus 1 and an n plus 2 in the denominator. So just like the standard ratio test, you do all of your manipulations the same way. The only difference is you do get to mind these x terms, x minus 3, quantity to the n plus 1s, or the x to the n's. And then once you get here, so we still need to compute the limit. And the limit's only with n's. So we're comparing here what's going on with our n's. We just have a degree 1 and a degree 1, which means it's going to go to the ratio of their coefficients, which means that the limit is just 1 for our n's. The x minus 3 term always is still going to hang out. And so we arrive at this equation, which is, of course, if we ignore the 1, just x minus 3 is less than 1. And so it is this constant. Once you isolate your x minus a, or some sort of absolute value of x minus a, then this constant is our radius of convergence. In this problem, there wasn't much else to do. So you can kind of imagine that if the ratio here, when I take the limit as n goes to infinity, if instead of getting 1, let's say I had like a 3 here, then I would have to divide that 3 over, and I would then isolate my x minus 3 less than 1/3. That 1/3 would then be the radius of convergence. Because of this problem, we didn't have any other constants to really mess with, so the radius convergence just stayed at 1. And so what does this mean? This means that we have essentially this inequality. We have -1 is less than x minus 3 is less than 1. And then to solve that, we can just add 3. So think of this as 2 inequalities. And so whatever we do with our standard inequality tricks, you know, we do one thing on the left side of the equation, we have to do it on the right. If you're writing it in such a way as having a compound inequality, you have to do the same thing on each piece. So since we're adding 3 in the middle, I have to add 3 on the right and add 3 on the left. And so what is our resulting system of inequalities here? We'll get 2 is less than x is less than 4. And so this is our interval of convergence. If we were to draw it on a number line, you can kind of see here's 3, so here's our center, and we know we will converge between 2 and 4. So you can kind of see if this were, you know, a circle in one dimension, the radius is 1 about x equals 3. So we go 1 on the right and 1 on the left. We do need to check the endpoints. So this is something we didn't get to talk about yet. So why do we need to check the endpoints? Well, the ratio test tells me that if we are strictly less than 1, if these ratios for the whatever x value we plug in, if it's less than 1, it'll converge. So we know these values are good. The question is though, but if x equals 2 or if x equals 4, you can kind of check here. What happens if x equals 2? We will get a -1, but then in absolute value, it'll become +1. And then when I compute the limits of my n, we'll still get 1, and we'll get equal to 1. That gives me an inconclusive ratio test, excuse me. So what we have to do is potentially use other tests to determine what's going on at the endpoint. So let's write that down. So at the endpoints, the ratio test is inconclusive. So we need to use other tests to determine convergence. Is it all on the screen there? Yeah. So let's see what that's going to do. We have our function. And we need to check x equals 2 and x equals 4. So what are we going to get? F of 2 is going to be 2 minus 3 to the n over n plus 1. And if it helps, write out the first few terms of the series, and then plug in the value. I would say you want to then try to practice of kind of manipulating series as they're in their series form. It's a good skill to have, and it will help you save some time. But when you're first learning these, it really helps maybe to write out, like we did with the first problem, our f of x is 1 plus x minus 3 to the 1 over, when n is 1, the denominator is 2, x minus 3 squared, when n is 2, the denominator is 3. And write out the first few terms, and then plug in 2 if you'd like. And we will get 1. This is going to be 2 minus 3, give me a negative 1. 2 minus 3 will give me negative 1 squared, gives me a positive 1. And then hopefully you can kind of see what's going on with this guy. What do we have? This is just the alternating harmonic series. And of course, if we took this guy here and then just simplified using the algebra in the sum, well, we'll just get minus 1 to the n over n plus 1. And so what is our conclusion on this? Will this converge? Is 2 a valid number to plug in there? So it's just the alternating harmonic series, so it is an alternating series. And what's happening to the terms? They are decreasing. So f of 2 converges by the alternating series test. In other words, we can keep 2 in the domain. Or the interval of convergence. Okay, so one endpoint is good. We want to check the other endpoint as well. What's going to happen with f of 4? We will have four minus 3 to the n over n plus 1. And if we just do our algebra within the series, what's going to happen? We just get 1, now positive 1 to the n, which is just 1. And so we will get 1 over n plus 1. And of course, if you would like, we can write out the terms. We'll just have 1 plus 1/2 plus 1/3 plus 1/4, etc. In this case, it's a harmonic series. So it diverges. In other words, when x equals 4, we can't include it. So if we were to kind of summarize what we just found, we would say that the radius of convergence, or let's call it the interval of convergence, for this function is then going to be, I can include 2, but not 4. And of course, if we want to write it in interval notation, square bracket around 2, open bracket around the 4. Any questions on that? Anyone still writing? Okay. Okay, so that one wasn't too bad. I mean, the series itself was just shifted, about 3, but the ends, the function involving the ends for your coefficient wasn't too complicated. Let's do one with the factorials. This is a really weird function. These are called Bessel functions. This was pulled out of the book. I think they denote it with the letter J. Is going to be -1 to the n, x to the 2n over 2 to the 2n, and then n factorial squared. So this is about as complicated as they can get. So I want to kind of work through this and show you guys, where to focus kind of your brain on the different algebraic steps, because there's a lot going on here. We've got, first of all, what's going on with the exponent here? It's not just x to the n, it's x to the 2n. So that's going to change a little bit. We've got not only a factorial in the denominator, but it's the quantity of the entire factorial squared, which is something we haven't seen yet. I think this was kind of about the biggest point of mistakes, at least minor mistakes, is some people are still a little rusty on manipulating these factorials. On the midterm, we had something like a 2n quantity factorial. So I definitely want to go through more of manipulating those and give you guys some practice with that. And then, of course, we have an exponential here. It's 2 to the 2n. And, well, we've gotten pretty good with manipulating exponential functions. Those haven't been too big of a problem, but we'll see how to do this. The biggest things are we just got to be careful with the exponentials and the factorials with that an plus 1 term and making sure we're keeping our parentheses in the correct places to deal with the n plus 1s. Let's take a look at this function now. Let's actually write out a few terms. So when n equals 0, we should have, well, -1 to the 0, just +1. We will get x to the 0. We will get 2 to the 0, and then 0 factorial squared. X to the 0 is just 1, 2 to the 0 is just 1, and 0 factorial we define as 1. So the first term's 1. Let's check n equals 1. We will get -1 Now x to the 2 times 1, so it'll be x squared. 2 to the 2. And then 1 factorial squared. And so that's just going to give me a negative x squared over 4. Let's do a couple more. So n equals 2. We'll get minus 1 squared, which will of course be positive 1. When I plug in a 2 for n, that'll be x to the 4th over now 2 times 2 to the 2 times 2, 2 to the 4th, and then 2 factorial squared. So that'll give me an x to the 4th. That just becomes 1. We'll have 2 to the 4th times 2 factorial is 2. So it'll just be 2 squared. And if we wanted to simplify this a little bit more, of course, it's going to be x to the 4th over 2 to the 6th, or x to the 4th over, what is that, 64, I believe. If you guys are gamer fans at all, or kind of know history of gaming, you can kind of memorize the powers of 2 just because it's how all of the systems developed. Nintendo 64 is a 64-bit, right? Every bit is a 1 or a 0, so there's 2 options with 6 different positions, gives you 64. If you are really old like me and remember, NES and Super NES. So Super NES was 16-bit, regular NES was 8-bit. So you can kind of remember 2 to the 8th is 256. I don't know if anyone's ever played the original Zelda, but you can only get a maximum of 255 coins. That's because it's all the bits from 0 to 255 is 256 different numbers that they could store with that 8-bit system. Let's do one more. So n cubed. We will have a minus 1 cubed. We've got x to the 6th now. So we'll have that 2 times 3. We will have 2 to the 6th, and then 3 factorial squared. And the coefficients in the denominator are going to get really, really messy. So our 2 to the 6th, again, was 64, but our 3 factorial was 6 squared. It's usually easy enough to just keep them as they are. You could even keep them written like this. I also often like to just keep, especially factored things like 2 to the 6th or 3 to the some power. It's easy to keep those as they are. So let's just take a look at this function. Let's write out our terms. What do we have? Our first term was 1 minus x squared over 4 plus x to the 4th over 64 minus x to the 6th over, let's just keep it as 2 to the 6th, 3 factorial squared. And so what's kind of the pattern here? We have a polynomial. It's, again, an infinite degree polynomial. But by having this 2 to the n in the exponent, we're kind of dictating that I only want even powers of x. So the next one's going to be x to the 8th. And then you should notice that, well, this exponent and that exponent are the same. So I should have a 2 to the 8th, 4 factorial squared. And then, of course, we've got this minus 1 to the n. And so those are going to alternate as well. So maybe, once you guys practice writing out a few terms, you can kind of get the hang of what's going on and kind of see a pattern for this polynomial. So this is our function. And we want to, again, determine the radius of convergence, the interval of convergence for this guy. So let's go through our steps. So step 1, this is kind of like step 0. If you want to get an idea of what this function is doing or what it looks like by writing out the first few terms, really encourage you guys to start off doing that as you're first learning these power series and Taylor series. The first step in determining the radius of convergence is to, well, compute a ratio, right? So we want to set up our ratio test. So our an minus 1 to the n x to the 2n over 2 to the 2n n factorial squared. Our a n plus 1 is what we want to be careful about. So it's going to be a minus 1. N plus 1 is entirely upstairs. X, that 2 needs to be factored out because we are replacing that whole n. You can kind of think of a parentheses around that n. And we should have a 2 x to the 2 times n plus 1. And likewise for this 2 in the denominator. And then this factorial is going to be a little tricky because we need an n plus 1. That whole thing needs to be factorialed. And then that whole thing after the factorial needs to be squared. So we want to set up our equation. We want the limit as n goes to infinity of an plus 1 over an. Then take absolute values. And of course, we need that to be less than 1. So I'm going to write that out with what we have above first. So looks like this is going to get a little messy. So let's just be careful with everything. Minus 1 to the n plus 1. X to the 2 n plus 1 over 2 to the 2 n plus 1 n plus 1 factorial squared. That's our numerator. That was this an plus 1. We'll have a big division sign, and if it helps, make it bold or whatever, to let you know where the bigger division sign is. So my an is now going on the denominator. We've got a minus 1 to the n. We've got an x to the 2n, 2 to the 2n, and our n factorial squared. And if it helps, I would put these individual guys in parentheses as well, so it's kind of clear where the numerator and where the denominator is, and we want to set that less than 1. So it's a complicated mess at the moment. It starts to get easier right in this next part. One thing I will say, I think most people kind of caught on this with the ratio test. Anytime you have an alternating series, these minus 1 to the n's or minus 1 to the n plus 1s, yeah, you can simplify them if you want in terms of the powers of minus 1 to the n. But because we're taking an absolute value, you can always ignore them for the ratio test part. They're just going to be, absolute value is going to get rid of the minus 1s. So we don't have to worry about that. It'll save us a little bit of space in writing. We've still got the limit as n goes to infinity. And now we've got our numerator. So I'm just going to have x to the, I'm going to distribute that, 2n plus 2, divided by 2 to the 2n plus 2. And then this factorial, unfortunately, can't simplify or anything yet. So that was our numerator. And then I multiply by the reciprocal of the denominator. So now I'll have my x to the 2n. I will have my 2 to the 2n. And then n factorial squared. Normally in a ratio test, I would say you can ignore the absolute values here, because as soon as we get rid of the minus 1s, the absolute values usually don't matter for just a standard series. But because we're doing a power series, right, we still have these x's. We have variables in there now. And because the x's can possibly be negative, we still need our absolute values. And we need that less than 1. So let's manipulate it. Let's keep our limit here. If it helps, match up your like terms. We've got x to the 2n plus 2 over x to the 2n. Everything's all multiplication, so we can put them in a different order if we want. And so let me write all that out. Go through it a little quicker. And so what's going on here? My 2n's are going to cancel there, because this will just be x squared times x to the 2n. So we'll be left with x squared there. Likewise here, those 2n's will cancel, so I'll be left with 2 squared in the denominator. And then the factorial ones are the tricky ones. The smaller one you always want to keep as is. So since it's n factorial squared, we're just going to keep that one as it is. It's the bigger one that we have to manipulate. Ignore the squared. The squared is what the operation comes last, right? We have to do factorial first, then our squared. So let's only worry about this factorial. N plus 1 factorial, we can factor as n plus 1 times n factorial. And so let's simplify. We've got the limit as n goes to infinity. And this is a good step to any constant. So keep any term with your x's over on the left. We want to start moving the constants over to the right. And actually a good idea to do, once we simplify this, we'll move the n's over to the right as well and send the limit over there as well with those guys. So we've got our x squared. Let's simplify these now. We've got n factorial, whole quantity squared. When I distribute the squared, this is just a product. We will have n plus 1 quantity squared. And now the quantity n factorial squared is less than 4. And I multiply that guy over. And now, this is saying take a number, factorial it, then square it. This is saying take a number, factorial it, then square it, both in the numerator and denominator. So those will cancel. And we are simply left with this expression. Absolute value of x squared. So this is 1 over n squared. Let's go ahead and send it over to the right. So we will have 4 times n plus 1 quantity squared. And we need to send our limit over here too. Does everyone see how that works? So we are just treating the n's. The n's are constants. So we can send them over, we can multiply them over to the other side. They are positive constants as well, right? So I don't have to worry about changing the inequality or anything like that. And then, of course, I still want to compute the limit as n goes to infinity. And what's going to happen? If n goes to infinity, we get infinity. So in other words, absolute value of x squared is infinity. To be a little bit more rigorous with this, well, this is absolute value of x squared. So this might come up in a future problem where maybe this is a finite number. We actually want to say something like absolute value of x, or absolute value of x minus 3, like we had in the last problem, right? We want to isolate this absolute value of x or absolute value of x minus 3 term. Well, this is absolute value of x squared, so we could take the square root of both sides first. So it would still just be absolute value of x. Squares and absolute values, they commute in some sense, so I could take absolute value. I can move the squared outside the absolute value if we wanted. Then, excuse me, take a square root. And when I take a square root of the right side, what do we get? Just 2n plus 1. The limits through all of this just hang out. Since all the operations we are doing are continuous, the limits essentially just commute with everything, and we can just kind of keep them hanging out there. So I would take a square root of both sides first, and of course, we would get absolute value of x is less than infinity. And of course, you could have kind of gone from here. Well, if absolute value of x squared is less than infinity, it's a little more hand-wavy. If I take a square root of both sides, square root of infinity, still infinity. And so you could have just concluded that our absolute value of x is less than infinity. What does that mean? Anyone still writing? So we need a new page here. So what does that mean? This means that our interval of convergence is this. Essentially like how we had the last problem. Whenever we have absolute value of x is less than infinity, or absolute value of x is less than any number, it just means x is going to be in between negative that number and positive that number. So less than the positive, bigger than the negative, whatever that number is. And if that number happens to be infinity, it literally means that the interval of convergence is all real numbers. Any questions on that, guy? So we will see this a lot. Whenever there are factorials in the denominator, what's kind of going on here, just to help develop your intuition? With our function, these powers of x, even if it's just even powers, as we kind of saw when we wrote out the terms, these are kind of growing like a geometric series. But what did we show that grows faster than geometric series? Factorials do, right? So even though there's this sort of geometric series based on our powers of x, whenever we have factorials in the denominator, it's often the case that we will end up with an interval of convergence of all real numbers, just because factorials grow so big so fast. And we saw this with e to the x. So let's expand a little bit upon what we've been doing, and then there's an activity for today that I want to jump into for a little bit. So far we started with Taylor polynomials and showing that, well, if I have a function, if I want to approximate this function with a polynomial, I have this way of creating a polynomial based off of its derivatives and finding its coefficients. And the more and more degrees we include, the more and more derivatives we include, the closer that approximation is going to get. And then we kind of switched gears. We jumped in from the opposite way and said, well, what if I just start with an infinite polynomial? These are our power series. What happens with these infinite polynomials? Can we get some notion of convergence out of them? Can we get a notion of where they are well defined? And as we kind of just saw, yeah, there's a lot of functions we can actually define this with. And so the big idea now is kind of tying these two together, which we will actually get. And if I instead, so if we kind of started from the first approach, like we were doing on Tuesday, if I want to approximate a function with a polynomial, what if we wanted to approximate it with an infinite degree polynomial? In other words, can I come up with a power series that actually represents a known function? This is kind of our question now, when we want to tie these two ideas together. And of course, the answer is yes, but we might have to restrict domain. So for example, on the project on Tuesday, we were coming up with Taylor approximations with our favorite exponential function, just e to the x. And what did we find? We found that as I take derivatives, should have been finding something like this. I think the project, most people got up to 3. And we notice that, well, the more degrees, the higher degree polynomial I want to take, the coefficients were just, or the derivatives at 0. Of course, we should actually specify at x equals 0, since we're taking our polynomial centered at 0. Of course, when I take successive derivatives of f of x, we just get still e to the x. And then when I plug in 0, what do we get? We just get 1s. And by our formula that we derived for the coefficients is that you would take the values of those derivatives. So to write this out a little bit more rigorously, this is f of 0 plus f prime of 0. 1 factorial. This is our generic formula for finding these coefficients, for finding the constants that determine a Taylor polynomial. I would take the derivatives, evaluate it at whatever point we are centered at, and then divide by n factorial. And I'll leave this to you guys to check, that we can actually represent e to the x. If I continued in this way, we would have more and more powers of x, and we can actually do that all the way out to infinity. So we have this well-known function, e to the x, that I can also represent as a power series given by this guy. And I'll leave this to you guys to check. What should the radius of convergence take? Check the interval of convergence. So we should find minus infinity to infinity. I don't want to go through the calculations again for finding the interval of convergence. I'll leave that as kind of a small homework just to kind of check your own understanding. Follow the steps we did on the last one. And this one's a little bit simpler. It's just got n factorial in the denominator there. And you should find, well, e to the x, what's the domain of e to the x? All real numbers, minus infinity to infinity. And it's nice that, well, I have this power series now where this power series works for minus infinity to infinity. So it doesn't matter what number I pick. If I actually want to compute e to the x, we can actually use this formula of the power series to approximate it, and then just stop after however many degrees of accuracy we want to get. Well, what about some other known functions? The other most common formula that we have seen, if I say, does this series converge, or if it converges, find the actual value that it converges to. There's only two things we could do. It's either a geometric series, because we know how to actually compute the values that they converge to, or it's a telescoping series, and we've got to do some sort of fancy tricks. Well, telescoping series, fancy tricks, they only work on small cases. But the geometric series, we actually have a formula for it. Namely, that we have this correlation. So our n here is starting at 0, so it'll give us that 1 in the numerator. And we have this relationship. Well, this isn't, what did we say r could be in this case for a geometric series? R could be between -1 to 1, right? And well, this r is just an r. It's kind of a dummy variable that I can put in, so it's not, a big deal if we just define our function. Let's call this function g of x as 1 over 1 minus x. But we need to be careful here with this statement that I wrote on the right. Because if I just give you this function, this 1 over 1 minus x, this is a typical function you might see in Calc 1, compute derivatives, find intervals of increasing, decreasing, all that kind of stuff. What's the domain of this guy? The domain is all real numbers except x equals 1, right? Whenever we have a rational function, if we don't explicitly state our domain restriction, then we assume that it's as big as possible. So all real numbers except wherever it's going to be undefined, wherever the denominator is 0. So the natural domain for this guy is everything except x equals 1. But that's a little problematic, right? Because when does this guy converge? Well, you could go through the interval of convergence test again, which is just essentially going to be repeating the exercise that we did originally with the geometric series. So here, this equality only holds for x in between -1 and 1. So what we're going to see is it's nice to be able to represent functions as power series, but we just have to be careful of when is that power series valid to represent the function, right? If x was 2, well, this would give me 1 over -1, which would give me a -1. And of course, if I have a 2 here, well, it's going to be 1 plus 2 plus 4 plus 8. And of course, if I add up all those numbers, I will get infinity. It's not going to equal -1. So the equality is only going to hold in the interval of convergence, which is a big reason why we want to find these. Okay, so any questions on that? So let's take a look at the activity. What we're going to see is, well, why do we care about this? And we want to get into why we care about power series. And really the idea is, well, Taylor polynomials we kind of saw give us approximations to numbers that might help us compute values that we don't know how to compute. It could give us a way to program a calculator to compute things that are hard to compute. But as well as it'll give us another technique of solving essentially differential equations. It'll be a little bit beyond this course, but even in the basics, what we might want to do is be able to integrate and derive functions. So before we get to there, we might want to find new ways of representing a function. Let's say with known power series. So maybe we'll get a list going next time as we work through more of these of known functions and their power series. It might be a good idea to kind of keep a list going. Right now, let's only focus on this guy. E to the x is another one we'll be working on for the project for today, or the activity. It's just going to involve this formula here for our geometric series. And let's suppose we modify that a little bit. Let's suppose we have some function that is now, let's say, 1 over, let's say 1 minus x squared. And if we want to do anything with this function, well, I can compute derivatives, calc 1, derivatives are straightforward, product rule. What if we wanted to integrate this guy? It almost looks like an arc sine, but there's no square root there. And so integrating it, we could try to do a trig sub, and it would be kind of technical to get through. What we can actually do is kind of make a note that it's just a composition of functions. It looks a lot like that 1 over 1 minus x, except there's just an x squared. So let's call h of x our 1 over 1 minus x. And if we just compose those, we get the function we want. And so if we have this power series representation for h, pretty easy, right? Just x to the n. Well, what should h compose g of x be now? So again, it's just a practice in composition. Well, g of x was x squared, which means wherever we have x's for h, we want to put x squareds now. And so what does that give us? Something like this. Just x to the 2n, and of course, if we wanted to write that out, it's going to be 1 plus x squared plus x to the 4th plus x to the 6th, and keep going up by even powers. So we get this infinite polynomial of now even degrees. And that's kind of nice because, well, now if I want to, say, integrate this guy, we will actually get to the fact that I can actually just integrate term by term for the power series. Even though there's an infinite number of terms, we can just integrate all of them following the formulas for n, and it's pretty easy to integrate just that guy, right? And then we can come up with a new power series for the integral of h, or excuse me, the integral of f, of h composed g, which might be hard to do otherwise. Does that all make sense? Kind of a basic idea? Okay, so go to, I think this is another problem with the, oh, sorry, there's some in chat. I did not have that chat up. Interval of convergence, radius of convergence, got that. I'm from that era. Any other questions? I think I addressed those questions in the lecture. Sorry for missing those.